Hi, my name is Frankie, and I'm an assistant professor at the University of Hawaii. I'm going to be talking to you about active learning in this four-part video series. This video is going to introduce the topic, and then we'll talk about maybe some reasons why you would want to use it for your application. Active learning is a semi-supervised machine learning method that iteratively samples a dataset to learn a target-output distribution as a function of an input space. Let's break each of these components down into a little bit more detail. A semi-supervised machine learning method is a type of supervised learning. You may be the most familiar with passive learning, which has this label, but essentially it's where you already have your entire dataset and it's labeled. We will call the dataset D, and it's equivalent to D sub L, where L equals labeled. In active learning, what's different is that D, your data set, consists of not only some labeled data set, but it's a union of unlabeled data as well. So some of your data is labeled, and you have access to unlabeled data. The next part is this iterative nature of active learning. Here we have a graphic example that I'm going to walk through that might make a little bit more sense. This subplot, these 9 subplots, demonstrate the iterative sampling of some random sampling strategy. So you'll start out with some initial data set. Let's call it big D sub I, where I stands for the iteration. The iteration, in this case, I is equal to 1. The next iteration, you sample a new point. In this case, it's this blue dot over here, and that is little d I, where I is equal to 2. Okay, and so on, you sample a new point and you add it to your big data set D. Your job then, as the active learner, is to learn a target output distribution as a function of an input space. Using that previous example, the input space in this case is the location of the dot. It can be an XY coordinate, and then the output is the class of that dot. It's blue or orange, depending on the color of your screen. Your job then is to learn this boundary that separates blue from orange dots. So in this case, your data set, your labeled data set, it consists of training pairs of input and output, where input, remember, is position and output is class. If you were to be even more specific about what the input and output pairs look like, each line item broken out, this is the first data point, where it's the coordinates of your first data point and then the class of your first data point. And then the next line item, your next training pair, is the position of your second data point and the class of your second data point. And you want to append all of these training pairs together to make up your data set, your labeled data set. Your job then is to learn a functional mapping, let's call it f hat of x, that transforms your input label data to your output. And we're hoping that this functional mapping approximates the true function that generated the transformation from your input x to output y. Why would you use active learning? I'm going to demonstrate this with an example where on this side we have the example we saw of a random sampling strategy. And again, we're going by iteration. So the top left is going to be your first iteration, and then your bottom right is going to be your 9th iteration. And we'll just go left to right, row by row. On this side, we have an active learning strategy where we're actually using the information from previous iterations or your labeled data set to inform where to sample next. And what you'll see that, yes, in the first iteration, we start the same as a random sampler. This is our initial data set. But we start to differ in the second iteration where we sampled this orange data point. And so a little intuition as to what's going on in the back end. This is an uncertainty sampling strategy where feasibly the points that are closer to your decision boundary are probably going to be more uncertain. And so the active learner chose that point that was informationally dense characterized by how uncertain the active learner was, and then labeled it. And then the third iteration, we see a pretty similar strategy where we sampled a blue dot that was really close to the boundary. And what you'll see is that by the fourth or fifth here, this fifth iteration, the decision boundary doesn't really change anymore. And that's called convergence, when your model has converged to a solution and doesn't stray away from that. Whereas in the random sampling strategy, that decision boundary continues to move and move, so it hasn't really converged on a good solution. That's another thing, good. In this case, good means accuracy. And the active learning strategy using uncertainty does come up with a good decision boundary, and that decision boundary accurately separates the orange from the blue dots. Whereas in the random sampling strategy, that decision boundary does not do such a good job. Another reason why you would want to use active learning is if you have a very expensive sampling campaign. I'm going to use the example of the Mars 2020 mission, where it took billions of dollars to build this rover, and then we had to launch it, and then once it landed on the surface, we wanted to make the most of its finite lifetime. Well, one way of doing that is to collect really informationally dense samples from scientifically interesting spots. So this is an application where active learning makes the most sense, where if you can minimize the number of samples that you have to collect to get a good model or understanding of your environment, then you can minimize the cost associated with labeling. And then finally, a couple other reasons why you might use active learning is that it improves generalization across your input and output space, and it's robust to noise. An argument in favor of generalization is, let's say that you just have a random data set. The way that it was sampled, let's say, preferences this regime of information, this input space, and maybe it underemphasized this other regime of space. Well, we saw in the previous examples that active learning uses information in a way that either maximizes uncertainty or we'll talk about other kind of sampling strategies later, but inherent in those kind of sampling strategies is almost uniform distribution or increasing diversity of the samples that you are taking in and labeling. And with that, you can improve generalization because you're not overemphasizing or underemphasizing different spaces. You're just right emphasizing the space. And that last point, robustness to noise, active learning methods have the ability to incorporate statistical methods. And so if you can incorporate uncertainty and probability, then you can characterize noise and build it into your model, whereas a lot of other machine learning methods don't have statistical methods built in. In the rest of this video series, we are going to talk about the algorithm components that constitute active learning. Of the algorithm components, two of the most impactful components are the learning model and the query policy. So we'll talk about different choices for learners and query policies, and then we'll end with applications and limitations. I really want you to walk away with an understanding of where active learning may be best suited, what kind of applications, and then once you're comfortable implementing it, understanding the limitation of the benefits you could gain. So I hope that you join me in this journey. See you next time.